Okay, so as promised, we are going to work on the cross product in this video. We're going to have a couple videos on the cross product. This is the first one. So I will attempt to share my screen and we'll see if this works. This is looking promising. All right, so unlike the dot product, the cross product is an operation between two vectors, let's call them u and v, that results in a third vector, let's just call it w, that is orthogonal to both u and v. So how are we going to do this? Well, for w to be orthogonal to both u and v, we know that the dot product of u with w and the dot product of v with w both have to be 0 from what we've talked about in the dot product. So it must be true that this system of equations has to be satisfied. And so what we're going to do now is we're going to multiply the first equation by v sub 3 and the second equation by u sub 3, and then we're going to subtract them. And when we subtract them, we are going to get, after a little bit of algebra, this lovely looking equation that I am writing right now. So I encourage you to do this one on your own and see if you can have fun just like I did. All right, so we get this equation. So now if we're assuming that the coefficient of u sub 1, the coefficient of w sub 1, this guy is not 0, we can divide by it and we can solve for w sub 1. And so when we do that, we're going to end up with w sub 1 is going to be negative of, well, the coefficient of w sub 2 goes in the numerator and the coefficient of w sub 1 goes in the denominator. W sub 2 is a free variable. By free variable, I mean it can be anything. So the most convenient thing to let it be would be the denominator or the negative of the denominator, in which is what we're doing in this case. Because if you multiply by the negative of the denominator, you just get the numerator. And so by using this expression for w sub 2, we easily get w sub 1. Now you can check that even though we assumed that that denominator or the coefficient of w sub 1 was not 0, if you plug these solutions into the equation, either one, you will still get something, either one. If you plug it into the equation, you will get that it satisfies the equation. And then we can very easily solve for w sub 3 by just plugging into either the first equation or the second equation from our original system. And so we get this lovely expression for w. So this gives us the definition of the cross product. So if u and v are given, then their cross product is the vector. No, I did not memorize this equation. No, you do not need to memorize this equation, but it's good practice to write it so that we know, what it really is. And there we go. The direction of the cross product is determined by the right-hand rule. And that's illustrated in figure 2.54 of the textbook, and I reproduced it in the notes conveniently, so while you're listening to the video and looking at the notes, you don't have to go back to the textbook. Again, do not memorize that equation. I have not, I will never, you will not need to. And so we're going to do something that will give us a way to nicely, I'm going to say easily, but well, more easily than memorizing the equation, to do the cross product. So we're going to hold off on doing examples till then. So there are some cool properties of the cross product. First of all, the cross product is anti-commutative. And that kind of makes sense because of the right-hand rule, right? So if I have u cross v and it's pointing up, well, when I do v cross u, I'm looking at starting with v and crossing going to u. Notice I'm pointing down. So the cross product u cross v is the negative of v cross u. And the distributive properties hold. If I take the cross product of a vector with the zero vector, I get the zero vector. If I take a cross product of a vector with itself, I get the zero vector. And we can also define the scalar triple product, which satisfies that equation, which on the face of it is clearly non-intuitive. We're going to talk about the scalar triple product when we talk about applications. But without calculation, we can determine the cross products of the unit vectors, right? Because the cross product gives an orthogonal vector. So we can use the right-hand rule. So if I have I, which is the x-axis, positive x cross j, positive y, my thumb's pointing up, I get, k, because that's positive z. Similarly, if I do j cross I, my fingers are on the y-axis, and when I take the cross product, my thumb's pointing down, which gives us negative k. What about j cross k? So j, my fingers are on the y-axis, and I'm going towards the z-axis, and my thumb is pointing to myself, and well, I'm just positive. So that's the positive x-axis, so that's positive I, and you can do the same thing for all of these. So let's do a quick example sort of using that idea. So I want to find the cross product of the vector 2 times I with the cross product of k with j. So let's do the cross product of k with j first. So we can either look at the table or just think about cross product of k with j means I'm pointing to u, which is the negative negative x-axis, so I get negative I. And so that tells me then that 2I cross product k cross j is really 2I, take the cross product of negative 1 times I. So that's going to give me a negative 2, because we could take the scalars out, times the cross product of I with itself, but that's just the zero vectors. So my answer is the zero vector. Now there's a nice theorem involving the magnitude of the cross product that's kind of similar to what we had with the dot product. So let's suppose u and v are vectors again, I know you're shocked, and let theta be the angle between them. Then it turns out that the magnitude of the cross product of u with v is equal to the magnitude of u times the magnitude of v times sine of theta. So that's pretty similar. Just remember we did the dot product, since that's a scalar also, but it's times cosine. Anyway, to show this is true, all we would do would be take the magnitude of u cross v squared, kind of like we did with the dot product, which is the u cross v dotted with itself, and go through the same argumentation in a similar way that we did when we did the dot product. And of course, we just use the property that sine squared theta is 1 minus cosine squared theta, and we get it. Now, as I promised, sort of the shortcut way, the easier way to compute the cross product is using the determinant, because if we do that, we don't need to memorize that really horrible definition, and it's all good. So for our purposes, an M by N matrix, M as in Mary, N as in Nancy, is just an array of numbers with M as in Mary rows and N as in Nancy columns. If the number of rows and columns are equal, we call the matrix a square matrix, and we have some things that we can only do with square matrices, such as the determinants. So for 2 by 2 matrices, how do we define the determinant? So we take the product of the top left and bottom right entries, and from that we subtract the product of the bottom left and top right entries. And that's the determinant of a 2 by 2 matrix. Now for a 3 by 3 matrix, things are a little more complicated. There are various ways to find the determinant. One of those ways is to sort of copy the first 2 columns and then do products just like I did for the 2 by 2, starting from the left, going down diagonally to the right for the first row, and we add all those up. That's why I put them in green. And we go the other way from the third column, third row, do all of those diagonally up, and those are subtracted, which is why I put them in red. But a more convenient way for our purposes to take the determinant of a 3 by 3 matrix is to use what is known as an expansion along the first row. So how does that work? So let me just reproduce the matrix here, since I didn't give myself that luxury, or you, of putting it in. And what we're going to do is we're going to sort of focus in on that top row. All right, so how this works is we look at the first entry, we take the first entry and multiply that by the determinant of the matrix form by wiping out the first row and first column. So B sub 2, B sub 3, C sub 2, C sub 3. We subtract the middle entry, and again, we're going to knock out the first row, but this time we knock out the second column. And so the matrix is going to be the 2 by 2 matrix whose first row is B sub 1, B sub 3, and the second row is C sub 1, C sub 3. And last but not least, we look at that third entry and we wipe out the third column in the first row. And so our matrix is B sub 1, B sub 2 in the first row, C sub 1, C sub 2 in the second. And if you go through and evaluate all those determinants, you're going to actually get the same answer. Now, what the heck does this have to do with the cross product, you might ask, and here we go. So what we do for the cross product is we put the unit vectors, just by name, is the first row, and then each of our vectors are inserted horizontally. So the components of U become the entries in my second row, and the components of V become the entries in my first row. And then when we apply that cofactor expansion, right, what's going to happen is we're going to have U2, U3, V2, V3 is our first matrix times I, minus U1, the determinant of the matrix whose rows are U1, U sub 3, and V sub 1, V sub 3, times J, plus the determinant of the matrix whose entries in the first row are U sub 1 and U sub 2, and in the second row are V sub 1, V sub 2, times K. We do that product, sum, and all that, and we get our answer. And if you do all of the work, you can compare, and you'll see that the right-hand side gives us the exact definition of the cross product. Phew. Okay, so you may want to check by sort of, putting the dots, dashed lines through the rows and columns to make sure that I did that right, because I'm only human. But before I stop recording, before we stop the video, let us do an example, because what is life without a good example? So let's find the cross product of these two vectors, A and B. So here's how we're going to do that. We're just going to follow the lead of our instructors. First row just gets the unit vectors, I, J, K. Second row is the entries of vector A, so 2, 1, 2. Third row is the entries of vector B, which is 1, 0, negative 1. Okay, let's take that determinant. Take that determinant, please. We're both too young for that. Okay, so again, we're going to do an expansion on the first row. So our first thing we're going to knock out is that first column. And so we're going to get the determinant of the matrix whose rows are 1, 2, 0, negative 1. And that's times I. And then minus, let's see, what is our matrix for J? And I recommend actually doing this to knock out to sort of remind yourself what you're doing in terms of which columns are not being considered, just it makes it easier. So let me see, that gives me first row of 2, 2, second row of 1, negative 1. And finally, my last matrix, I just knock out the third column, so that leaves me with the first row of 2, 1 and 1, 0. When I say just knock out the third column, I mean and the first row. Okay, so let's work this out. So I'm going to get the quantity of 1 times negative 1 minus 0 times 2 times my unit vector I minus the quantity 2 times negative 1 minus 1 times 2 times unit vector j plus the quantity 2 times 0 minus 1 times 1 times the unit vector k. So that is going to give me negative 1 or negative I plus 4 j minus 1 times k, or in component form, that's negative 1, 4, negative 1. And so that is the answer, and that's going to conclude the video. Suggested problems will be on the next video. Have a great day. Stop recording.